Hi, hello, I am a big goose, and today I kind of want to talk about quadratics. Not really how to solve quadratics, mind you, but more of understanding what quadratics actually are. What is a quadratics? And we're going to be doing this by kind of comparing quadratic functions to linear functions and kind of seeing how the two compare. We're going to be comparing them based off of their equations, their graphs, their tables, and of course, how often they call their mothers. Let's go ahead and start with So let's take a look at how the equations of these are going to compare. Now, this is going to look as though I'm giving you a lot more things than what I was originally talking about, which was about linear versus quadratic. And that's true. Those two are still our special ones that we want to take a look at. But we're going to look at all of these different functions because what you're going to see is this is going to have almost like a evolution of man kind of reveal. If you think of that picture of the evolution of man where it's like, it starts off with like a monkey hunched over, and then it's like slowly but surely it starts standing up until it's like some dude with a spear who eventually starts playing video games one day. This is very much like that. We are going to be evolving down in this direction for this. So the very first one I want to look at is called a constant. This is a constant function. Y is equal to 3. A constant is literally just any number. It could be 3, it could be 256, it could be 5, it doesn't matter. It's just saying that y is always equal to 3. It doesn't change over time. So this is like the most basic type of thing you could ask for. One step up from that, we're going to keep the same thing, y is equal to 3. However, for linear, we're also going to have plus x. This causes change. We're going to start at the number 3, and we are going to continue to grow by this amount here, whatever x is. That means that y is no longer always equal to 3. It could be equal to 4, 5, 6, 7, 8. It's going to grow depending on what is going on with this x. This is also our y is equal to mx plus b. You may not have recognized it because we don't have an m here. It's a 1, so it's kind of just chilling invisible. But this is a linear equation right now. Y is equal to mx plus b. So that's kind of where that comes from. It's just basically a constant, but we're adding a variable. The next step, quadratic. Again, our main focus, once again, we have y is equal to 3 plus x. However, this time we're going to take it one step further, and instead of just plus x, it's also going to be plus x squared. That's the only difference between quadratic and linear, is that we have this plus x squared. Now this pattern is going to continue to these later functions as well. This one, cubic would be y is going to be equal to 3 plus x squared, and then you might have guessed the next one, which is going to be plus x to the power of 3. And then finally, quartic is going to take it one step further, 3 plus x squared plus x to the power of 3 plus x to the power of 4. And again, you can kind of see this evolve as we start at the top with the constant, y is equal to 3, and each time it adds a new level of complexity. Again, the purpose of me showing you this is that I wanted you to see where you started, constant, what we're working on now, which is linear and quadratic, and then this is kind of what you go to later on, the cubic, the quartic, the quintic, the sextic, so on and so forth. But for right now, all we're really going to be focusing on is linear and quadratic. And again, to reemphasize, the only difference between a linear equation and a quadratic equation is x squared. If you see a variable raised to the power of 2, you automatically know it is quadratic. So we got 2x minus 3, and you can see our nice little equation here. In fact, let me go ahead and change this to, oh, that's interesting. It used to be projector mode. Now it's just now it's just big A mode, and that's just going to make everything bigger. And what is Braille mode? How do you have... Whoa! Whoa! What is this? What? How do you have Braille mode on this? That is crazy. Okay, I gotta look up how they do that later because obviously we're talking about something else right now, but that is very, very cool. Anyways, okay, so we have a linear equation, y is equal to 2x minus 3. I'm also going to write the same equation one more time, 2x minus 3. You'll notice that the blue line is sitting right on top of the red line. They are the exact same line right now. But now I'm going to make the blue line quadratic, and to make it quadratic, I'm going to have to do x to the power of 2. And that makes it quadratic. And you see that I would get this nice curve going on here. For those of you who don't know the exponent that I just put in here, if you want to do that on your computer for really anything, you can do Shift 6, which is the up caret, and that puts you into what is called the superscript up here, and then you can type in any variable you want. For us, it's going to be 2 because we're doing quadratics. All right, anyways, first thing I want to say, this creates a curve, obviously. The linear line is a beautiful straight red line, and a quadratic is a beautiful blue curved line. This curved line here, its technical term, is called a parabola. So this is matched up here. So the first thing I want to kind of go over is the similarity between these two. Both of these, you'll notice at the backs of them, have a minus 3 for their y-intercept. And wouldn't you know it, if you look on the graph at -1, 2, and -3, at -3, both of these lines cross the y-axis at that point. So these two both share a y-intercept. Again, like I said before with the equations, no matter what the equation looks like, the y-intercept for it is always going to be the one without the variable, okay? Now we have, that's basically where their similarities end. Now we're going to take a look at the differences. First difference I want to talk about is going to be the fact that if I were to zoom out, you'll notice that the red line doesn't, like, really change. It's kind of just chilling there in the center, right? As I'm zooming out into infinity. However, the blue line kind of got squished down into a singular line. It almost looks like it stops down here. If I was to hit the home button, bring me all the way, the home button, there we go, back to where we were, that's because a parabola has a minimum value. A linear equation does not have a minimum. It goes infinite in both directions. However, a parabola has a minimum value. If I was to drop a marble into this little curve, it would come down here and sit at the bottom. So it has a minimum value of this. That's something that's unique to that. Parabolas can also have a maximum value. If I was to make this negative, it flips the graph upside down. Notice the y-intercept is still the same, but now I have a maximum value. So you can have either a minimum or a maximum depending on whether it's a positive or a negative graph. The second thing I wanted to talk about that's different between the parabola and the linear equation is the x-intercepts. Notice that both of these have only one y-intercept. However, the parabola is going to have 2 x-intercepts. This is the x-axis. It crosses this line twice because it curves. It's the axis so nice, it had to cross it twice. The linear value only goes over the x-axis once, though. So the linear value has one x-intercept and one y-intercept. The parabola has one y-intercept, but it has 2 x-intercepts because it curves and hits it twice. Now let's compare the graphs of these different functions kind of the same way that we compared the equations of these different functions. Again, our main stars of the show is a linear equation and a quadratic equation. But again, I think it's important to know where you're coming from. You came from learning about constants, and you're going to learn about cubics and quartics one day. So, as for right now, though, we'll just focus on these. So, a constant, or y is equal to 3, that's the example of a constant equation. The graph of a constant is going to be a flat line because it is constant. There is no change whatsoever for a constant equation. It is 3. This equation is 3 here, it's 3 here, it's 3 here. It is always 3, and so it's a flat line. There's no change. A linear equation is going to have change. It's going to move up or down over time. So y is equal to x is going to have that change over time. It is still a constant rate of change, and so it is a straight line. Quadratic is not constant change. Quadratic is, of course, like we looked at earlier, is going to create that parabola, that nice big smiley face. So we are obviously still changing, but we're changing a lot there. Cubic is going to have an interesting idea where quadratic has one curve, cubic actually has two curves, where it curves once and then it curves a second time. Now, I am exaggerating some of these a little bit because it kind of helps you see what the patterns of these look like. And I also want to emphasize these equations don't look exactly like what I'm sketching up here. The idea is I just want to give you an overall broad interpretation of this. The last one, quartic, if this was one curve, this one was 1, 2 curves, this one's going to have 3 curves and is actually going to kind of look like the McDonald's logo. So x to the power of 4 has 1, 2, 3 curves and comes right back down to the bottom again, okay? But anyways, I wanted to kind of show and compare and contrast those things again. You don't necessarily need to know your quartics yet or your cubics yet, but knowing these first 3 is good. All right, so let's take a look at what these tables are going to look like between a linear and a quadratic. On the left-hand side, I have a linear equation, simply 2 multiplied by x. On the right-hand side, I've got a quadratic equation, which is x to the power of 2. So what I'm going to do is just kind of fill in these tables, and then we're going to try to look at what makes them different. Like, how can we identify a linear versus a quadratic? So if I was to take 0 as my x value and plug it into this equation, 2 multiplied by 0 gives me 0. 1 multiplied by 2 gives me 2. 2 multiplied by 2 is going to give me 4. 2 multiplied by 3 gives me 6. And 2 multiplied by 4 gives me 8. On the right-hand side for quadratic, we are going to be squaring the x value, so multiplying it by itself. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9, and 4 times 4 is 16. Now, right off the bat, you might notice, just kind of looking at these in general, you're going to notice a little bit of change here, but it's going to become evident when we look at the difference between the numbers. So let's take a look at their differences. From 0 to 2, there is a change of plus 2. So it adds 2 going from here to here. From 2 to 4, we also have a change of 2. From 4 to 6 is also a change of 2, and from 6 to 8, we also have a change of 2. So you can see that all of these are kind of the same. So let's take a look at quadratic now. From 0 to 1, we have a change of 1. From 1 to 4, we have a change of 3. From 4 to 9, we have a change of 5. And from 9 to 16, we have a change of 7. So 1, 3, 5, and 7. Right off the bat, you should notice that the change happening on the quadratic side and the change happening on the linear side isn't quite the same. For linear, it's consistent. Linear is constant change, 2, 2, 2, 2. On the right-hand side, there's still a pattern to it, but the change isn't constant. 1, 3, 5, 7. However, if we look at the change to the change, we're going to see this pattern crop up again. The difference between 1 and 3 is 2. The difference between 3 and 5 is 2, and between 5 and 7 is 2. So there's almost an extra layer of change for quadratic than there was for linear. And this pattern actually continues into the cubic and quartic relationships as well, the cubic and quartic functions, where you're going to see additional levels of change. Remember, quadratic was only 2 layers of change, so cubic is going to have 1 layer of change, 2 layers of change, and then finally a 3rd level of change until finally all of the numbers start being the same. For a quartic, or to the power of 4, it's going to take it 1 layer of change, 2 layers of change, 3 layers of change, and then finally, on the 4th layer of change, you're going to notice that this pattern starts to become consistent. And that happens with a lot of these functions as the exponents continue to grow. So, quadratic equations can be identified by a variable to the power of 2. Quadratic graphs make a U-shaped parabola and cross the x-axis twice. Quadratic tables have 2 layers of change, kind of like a lazy casserole. And quadratic functions call their mother every Saturday while they clean their house. That's it. Goodbye now.
Fun, you stare, nothing for an hour or two. Dropping a beat like 100 other artists would do. Clicking some codes like 100 other artists could do.